Hi guys, good morning, afternoon, or evening. I hope you guys have been enjoying the conference so far. My name is Olayemi Olabisi, and I will be presenting early stage epidemic forecasting. A little bit about myself. As I said, my name is Olayemi Olabisi. I am Nigerian. I recently completed a master's in big data analytics from the University of Liverpool, and I work in Wernicke as a SQL and a BI developer. Um, my research interest lies around forecasting. Uh, Forecasting is a very popular topic. It's used in most likely every organization, and can impact most aspects of our life in industry and society. So the topic is, forecasting early stages of epidemic. Um, Initially, I'll go through a bit of an introduction, um, try and give you guys a bit of background, a bit of history, and then we'll try and move on to the actual theory, which was applied to try and solve the problem. Leading on to that, we'll go on to how we actually evaluate and tested the theory against the problem, as well as other researches conducted to investigate more deeply the topic using a systematic review. Then we'll look at the results and also the conclusions and discussions around what we observed from the experiment. Epidemics, I'm sure we're all aware of, well, and pandemics, we've all at some point heard this in the last year or two. They've been around for a long time. Um, a famous example outside of coronavirus would be Spanish flu in 1918 and ended in summer of 1919. This virus killed over 50 million people, and back then there was no technology to really use to fight the outbreak. Fast forward to 2019, and we've got all kinds of technology. One of the tools we use is something called biosurveillance, which tries to use data to effectively detect these outbreaks quickly. Um, so previously we've used things like mortality rates, daily or weekly counts of selected lab results. Unfortunately, collecting, delivering, and analyzing these types of data takes a long time, so we're talking weeks and months. Whereas modern biosurveillance try to use less specific aggregated healthcare seeking behavior called syndromic data. So these are over-the-counter sales, pharmacy medication sales, school absences, complaints of individuals entering hospital departments. So those types of data can be analyzed within hours and days to detect spikes and alert the right organizations or authorities in order to then proceed to the next level, which is to find out, how infectious these diseases are through forecasting. Tabata in 2017 looked at the time series data of various disease outbreaks and identified different characteristics within that within a disease outbreak life cycle, essentially. And the part which we're going to focus on is the first takeoff period. It's identified as it exhibits a sharp rise in cases where numbers are initially dormant. So at the start of a disease outbreak, there's no There's no numbers, and then you see a sudden rise because the population is unaware, as well as the fact that you know these diseases are usually very infectious, so sharp rise is observed. And so during forecasting, um, there are standard steps to take when forecasting. The first step being to decide what to forecast, um, what units of measure, intervals, the period to be covered, etc. The next step is to clean the data and handle any issues in the data. So whether there's missing data, whether you need to adjust any population adjustments or units, those can be handled. And then the next step is to identify if any patterns exist. So cycles, seasonalities, or even no data, these can help in choosing the right models. And the final step is to choose the right models. Well, to choose a series of models and then evaluate those models based on either mean MAPE, mean absolute percentage error, root mean square errors, things like that. And again, the choice of um, criteria calculation can affect the model chosen in the end. So in early stage forecasting, early stages of epidemic forecasting, we want to know how many cases over the next days or week. When we look at the data, we see a very small sample of data. Um, Various studies use different sample sizes. So Fung in 2020 used a sample size of 8 to represent the early stages of epidemics. Wu in 2020 used 6 data points. So this varies based on different people. In this study, we chose 10 because it reflects um, reality. So coronavirus started in December 19, and 11 days later, WHO, World Health Organization, had declared it as a threat, and so that was 11 days. So I think it takes a little bit more than a week to for us to detect these things. So there are various forecasting methods to use. Unfortunately, they're not very accurate. So as we said, in the early stages, data is very limited, which makes this a small sample forecasting problem. Now, currently, there are three ways to address this problem in modern forecasting. The first is to use virtual sample generation. This method fills the information gap among each row of samples to stabilize the forecasting performance through adding newly generated virtual samples. In 2019, Ravuri and Vanos investigated the data generated by virtual sample generations and found the presence of top 1 and top 5 errors had increased by 120% and 384% respectively. And the presence of the use of the virtual sample generation didn't significantly improve the accuracy of the model. So, the cons outweighs the pros, I suppose. And another way around some small sample forecasting is the use of feature extraction, which excludes certain variables. But when forecasting in early stages, data is very small, so to exclude anything would be not be ideal, essentially. The final method is the gray system method, using the gray forecasting um, model, which is what we use in this study. So the gray system theory was developed by Professor Deng Julong in 1982. The name gray was based on the colors of subjects under investigation. For example, black box would refer to a system that is completely unknown. A white box would be referring to a system that is completely known, and the gray is meant to denote partially known and partially unknown systems, or a system with partially unknown information. While it was developing, he highlighted some fundamental principles of the theory as described. So some of them include principle of new information priority. So the algorithm tries to um, place a larger weight on new information as opposed to older information. Also, the principle of minimum information. So the theory makes use of minimal information, which is a sample size of 3. So for this forecasting model, you need at least 3 data points to make a prediction. There are various studies which have applied the model uh, to forecast in a wide range of fields. Um, One of those include uh, Chang in 2019, who applied an algorithm named EPGM11, which is an enhanced version of the gray model, gray forecasting model, to overcome the weakening of the latest datum problem with the traditional gray model GM11. So the EPGM11 was created using an alternative method for calculating the background value. It was then compared with the back propagation neural network as well as the traditional GM11 using TFT-LCD data from January 2010 to January 2012. The EPGM11 and the traditional gray model outperformed the back propagation neural network with a mean absolute percentage error of 4.46% and 10.9698% respectively. So the enhanced gray forecasting model outperformed the traditional GM11, and the GM11 outperformed the back propagation neural network. So there are various other studies which show that the gray models are great when data is very limited, as is the case with Chang's study. So, saying that the majority of the models used in research papers were enhanced in regards to the gray forecasting models, it inspired a study into the various methods used to improve the forecasting model to see which were relatively applicable to early stage forecasting. In this study, particularly, bearing in mind the restrictions of time and resource. So, using the Prisma guidelines, a systematic review was carried out um, based on the rigorous search and criteria implemented. A total of 13 papers were found appropriate and ideal and relevant. And out of those 13 papers, 38% improved the background value of the forecasting model. So that's the most popular method of improving the model and gaining higher accuracy. 23% used the multi-model approach, similar to an ensemble, and 15% enhanced the model by improving the accumulative generating operation mechanism. Some other methods were also employed, namely virtual sample generation and parameter optimization. So background values, in the gray forecasting models are very important parameters. They have a major influence on the performance of the model. They have two primary functions. One is to smoothen the data and strip it of randomness, and the second is to emphasize the importance of the newest data. The background values are also related and interact with something called A and B coefficients, which namely are development coefficients and the grade control variable. Um, so effectively, the A and B coefficients can influence the accuracy of the model. So by improving the background value, default, which is set to 0.5 normally, can have a compounding effect and drastically improve the performance of the model. The accumulative generative operational mechanism and its inverse are also important as they are responsible for reducing the variations and fluctuations of the original series. Um, Effectively, Professor Long, when creating this algorithm, um, assumed without proof that each and every component of the original sequence is positive and the class ratio of the first AGO is always smaller than the class ratio of the second. And this means that in some cases that is true, and that's when the algorithm works amazingly. Unfortunately, it's not true always. And in 2014, um, in 2001, Kun Li Wen um, recalculated this component of the algorithm and found made it a more generalizable aspect, but it's unfortunately it's not available um, for everyone. I don't think. Um, yeah. The other popular method was the ensemble, which is, it's a very popular technique to use in data mining. It's the combination of a group of weak learners in the attempt to leverage their different strengths to create a more powerful model with a which essentially then has a higher um, accuracy and forecasting power. So um, the next step was to then based on the results of the systematic review and all the restrictions that were in place, we decided to use the assembled method would have been the most ideal in this scenario because although the background value had more of an impact on the model, on the forecasting accuracy, as well as the AGO mechanism, in order to calculate and confirm the correctness of the calculations, it would have taken a lot of resources and time, whereas an ensemble is more straightforward and uh, more appropriate for this study. So the next step was to translate the algorithm from its mathematical form into R programming language, which is where the study will be conducted. And we used Tanji's tutorial, which was very instrumental in doing this. Once the calculations were in place, as you can see on the left, the algorithm there. I mean, one of the reasons why the gray system theory, these forecasting models are quite popular also is they're very, it's a simple calculation. Essentially, it's a very good model for cases where you just want to test and see. It's a quick, easy calculation. You can quickly test it and see whether it's applicable or not for any forecasting problem. And so once the calculation was done, was translated, all that was left to do was to make sure it was correct. And so by comparing the values gained from the R algorithm to Tanji's tutorial, we could confirm that it's the correct algorithm. And also, again, just to make sure that it's not just for those values, we compare different values, so different data points, different data sizes, and the same results were gained for all the different uh, samples. And then to further confirm, a MATLAB version of the algorithm which had existed before was also tested, and similar values were gained from that one also. So now we have the algorithm itself translated and validated. The next step is to identify which other algorithms to compare the GM11 with. And there are a vast number of algorithms out there, but currently the most proposed algorithm for early stage epidemic forecasting are growth models. Um, Growth models can be grouped into two types. The first groups are those with inflection points, without inflection points rather. Some examples include Brody models and negative models. The second groups are those with sigmoidal shape, and they pose a fixed inflection point. And some of these include Gumpert model, logistic models, and some others. In this study, we included the Gumpert model simply because it has an inflection point of about 37%, which makes it more suitable compared with the logistic models, which is the other popular growth model, but its inflection point is around 50%. And so once we have the models we would want to use, the data source, where do we get the data from, would be the next ideal uh, problem to solve. And you know, with the popularity of uh, coronavirus, there were vast data sources online. We wanted to use a secondary data source, which is a data source that already exists, because of the time we would be saving from data collection and aggregation. So from researching and looking around, there were three main sources that uh, looked reliable and other researchers and studies reference quite frequently. And those were the Johns Hopkins University data, the European Center for Disease Data, and the Health Organization data. Um, Through thorough investigation, we found that the World Health Organization data, they actually shifted the timing on the reports, which caused the data to have some type of overlap in the times. And so we excluded that the World Health Organization data for that reason. And effectively, we picked the European Center for Disease data simply because it appeared more complete. So it had some extra population adjustment columns in there, pre-calculated. Um, and so for this reason, it gave a clearer and more complete picture of the coronavirus, and so it was chosen. In terms of sample size, I think I mentioned previously, we chose to use a sample size of 10, so 10 data points, simply because it reflects reality a bit more. As I said before, it took 11 days for World Health Organization to announce coronavirus as a disease outbreak, as a threat to society. So 10 data points seem more reasonable compared to 6 or 8 data points used in other studies. In order for the experiments to be reliable, valid, and repeatable, we knew we wanted to run the experiments multiple times. And so we decided to use three varying countries' data to in order to improve the reliability of the results. And so it was about which countries to choose next. And so to choose these countries, there were many factors that were considered, including political influences, infrastructure, capabilities, corruption, and coronavirus timings. The biggest influence on the countries chosen is the quality of the data generated. And through observations, we found out that countries like China were hit heavily by the virus appear to have been unprepared. So the necessary actions required to adequately record and publish the coronavirus case numbers were not in place. So the data we see from them were very not ideal. So based on this, we decided countries that were infected after March 2020 are the most ideal countries to use. And so from that, we chose Haiti, Argentina, and Albania as the ideal countries to use. And so finally, the now that we have the algorithms and we have the data, it, the final thing to choose was the criteria, the evaluation criteria to compare the algorithms with. And there are several types of error evaluation methods in forecasting. Um, there are two main types. The first type is they are scale dependent errors. These methods can only be used for comparing algorithms when the data sets are in the same units. The second most common types are um, percentage of errors. So these are unit free. Um, there are a vast number of evaluation methods: mean absolute errors, root mean square error, mean absolute percentage error. And through research, out of all of them, we chose to use mean absolute percentage error in this case, simply because an MAP of 4% is much more readily interpretable than an RMSC of 256. It's just more intuitive. So next we see the results for all the algorithms for each country. So this slide shows how well the models fit and forecast the 80 dataset. Um, it can be difficult to visually try to discriminate the performance of these models. Um, One thing to note is that the polynomial neural network and the GM11 appear to be missing values, but these values are treated as inputs for the algorithms to use to then fit and forecast. On the x-axis, we see the number of days, and on the y-axis, the number of cases being predicted or actual. This slide shows the performance of the models against the Argentina data. Um, we can see that the performance of the models um, again can be quite difficult to distinguish um, and actually compare. Again, on the x-axis we've got the number of days, on the y-axis we've got the number of cases. And here we've got the performance of the models against the Albanian dataset. Um, on the x-axis again, we've got the number of days. On the y-axis, the number of cases. Um, on this particular one, as the days elapse, we see a much more difference in the performance of the algorithms, where it looks like the Gumpert model might have the best performance. But again, we'll check the actual values on the next slide. So this is the summary table. Includes all three data sets: Albania, Argentina, and Haiti. We can see the in-sample MAPE values as well as the out-of-sample values. So the in-sample uh, values is essentially evaluating the predictive capabilities of the models developed using observed data to see how effective the algorithms are in reproducing data, whereas the out of sample is looking at the actual forecasted values. Um, so also the ensemble here is um, a simple average ensemble. I mentioned previously that the ensemble is the most likely the most straightforward method to enhancing the GM11 model. Due to time and restrictions, we've opted to use this as an example to show that the GM11 can be enhanced this way. So by comparing the values, we can see that the ensemble performs better. The models in the ensemble is the GM11 model as well as the Gumpert model, because the Gumpert is one of the best performing models in this study. And so if we when we look at the numbers comparing GM11 Gumpert and polynomial neural network, we see that for Albania, Gumpert is the better model. With an in-sample MAP of 10.50 and an out-of-sample value of 11.16. For Argentina, the polynomial neural network outperforms the other two with an in-sample of 12.24 and an out-of-sample of 10.27. And for Haiti, so for the Haiti, the Gumpets would be the most ideal, simply because the it fits and forecasts reasonably well, whereas the polynomial neural network doesn't fit the data quite well, but actually forecasts uh, very well.